So this is, Vidya explained all this much better, this, through the quasi-particle interference, they do see this shift in the Dirac spectrum that is consistent. I'm going to wrap up. So here we presented a theoretical model for strain flat bands, space superconductivity. This demonstrates the role of these surface states. This opens a realistic route to strain-induced flat bands, because here we see how this dislocation array is a nice way of obtaining flat bands. And our model can account for previously unexplained experimental features. There are several other open questions that I'm not going to go into right now, but one thing that is interesting is the possible connection to interface superconductivity in other systems. For example, in STO, which we see is so important in those other examples of interface superconductivity, the structural distortions in STO seem to be playing a key role, and the conductance channels in STO are related to these structural distortions, as shown in this data from Ken Mulder's group. And so strain effects seem to be important all around. And then this is possibly that this mechanism could give rise to new states, possibly in these flat bands, or a way to its engineering. Thank you.
I was just hoping to get a little more intuition on the origin of the superconductivity. So I guess I have two parts. So usually you need to first pair electrons into Cooper pairs and then have the kinetic energy make these Cooper pairs condense. So in the flat band, I'm wondering, do you still get this kind of retarded pairing from phonons even though the particles aren't moving quickly? And then secondly, if you can glue them together, what makes these Cooper pairs condense rather than forming some charge density wave or some other kind of state?
So are you saying that the renormalization of the Coulomb repulsion by the bandwidth, this may not be there in this case because of the bandwidth?
Yeah, that's kind of what's the pairing glue part of the question.
So that's not very clear, and I mean, this is the question that we had as well, and Yang and I were also looking at what happens here, and so we have looked at some of this. What happens to the Anderson-Morel mechanism, basically where the bandwidth normalizes it, and there is still a bandwidth here because it's flat in a certain region close to the Dirac cone, and then there is still a bandwidth of the dispersing state. So, but it does act in quite a different way, and so we do actually get a different expression where there's a different. Where it's governed by a different energy scale, and so also I suppose you do see here that TC is not that high, so it could be one reason in which there still can be renormalization, but perhaps the scale is not very high.
So can I just summarize that it's kind of flat but not completely flat? So
yeah, it's flat in a small region. Sorry, I know there was another part of your question, but yeah.
Yeah, I had a sort of similar question, which is along the lines of once you have these flat bands, then any repulsion would produce the ferromagnetic instability, I think well before the attraction could take over. So do you have any thoughts on that?
A ferromagnetic instability? So what we have here actually is that we have these regions of, since these are already surface states, so they are already helical. In some sense, I mean they are already helical, and what we have here is that we actually have positive and negative magnetic fields, and so these are already there, and they sit on top of each other. So it's impossible for them to be further polarized because they're already positive and negative, and this is results from one time reverse, from one valley. And so then there's also the the electronic states from the other time reverse value. So you actually have opposite spins sitting on top of each other. So they can't further become ferromagnetic. Perhaps this is a pairing between the positive and negative regions that could allow them to pair.
Okay. I have a somewhat similar question. With repulsive interactions at partial filling, would you expect to get some fractional quantum Hall type physics, perhaps?
Because here we have flat bands, and
you have flat bands, and they are presumably topologically non-trivial, right? They have some term numbers.
Yeah. Yeah, so here, I mean, we said superconductivity simply because that's also what is seen, and then perhaps also the snake states could be helping in some kind of transport mechanism. But it is true that possibly looking within just the flat band regions itself, if there's some kind of commensurate filling, I mean, it seems to be. I mean, I don't see why not.
So still related question. So the flat band implies sort of you need some sort of real space interaction, right? Because flat band implies dispersion.
Right.
So, and what the mechanism of that attraction would be? So, where from you get the attraction?
You mean beyond just phonon-mediated attraction?
Yeah, phonon picture works well when we have Fermi surface index near the. So here it's a flat band, so dispersionless particles, and so something in real space almost naively causes particles.
Yeah.
Abstract.
Yeah, I agree that there's many questions or many open questions that come out of this as well.
First of all, we assume phonon mechanism. We assume we are attractive interaction coming from phonons. Question about repulsive interaction in these materials, the dielectric constant is very large at low temperature. So it can go up to 1,000, for example, in lead telluride. So we assume that the Coulomb interaction is strongly screened due to the large dielectric constant.
I'll follow up Drew's question. So suppose I give you a model in which I have a local attraction, but I have a completely flat band. And no matter what the gap is, the superfluid density is going to be exactly zero. So the DC is going to be zero. Okay? And if you have that basically show more of the recursive. And if you have not a completely flat band, you'll still have a very low superfluid density. That will determine DC, not the large gap.
Yeah.
That.
Oh yeah, sure. I think we discussed, and again here we don't have a completely flat band. That there is still dispersive state away from the Dirac cone, and it's true that here TC is not very high, and so it.
No, but TC won't even have any relationship with delta. That's what I'm saying. In a very flat band. It's not a BCF situation where the stiffness is huge and the gap is small. You're in the inverted situation. Okay, any other questions?
But if you say how do you estimate DC, so it's you estimate the binding energy or you estimate the coherence of the mutation?
Right.
Yeah.
Sorry.
just on the confirm side, I asked the media, so how large is your magnetic lens compared to the structure